Hi, everybody. I'm Alex Slocum, your introductory person. I first came to MIT in 1978. Fun place then, still a fun place. And I've had the pleasure of, teaching here for 40 years, on and off again. Been in MECE since 91. And all the students have been wonderful and colleagues and everything. And then a couple stand out. There's a bunch of faculty members in this room who I've had the pleasure of having in my lab. One of them is my boss. So if he fires me, I'll revoke his doctoral thesis. But another one is our special guest, Shoya Attar. And he came here 2000, was it?
2000, yes.
Yeah, 25 years ago.
Exactly 25 years ago.
And he shows up at my office and basically says, hi, I want to come here. I have a master's in Rensselaer, and I want to learn how to design machines, and some other words that basically affect is he only knew math and mechanics, but he wanted to learn how to do real stuff.
Design. But tell them what you said when you saw me.
What did I say?
You asked me if I was a FedEx guy. And I said, without a package? What kind of FedEx guy would show up without a package? But anyways, that was my first conversation.
Did I ask you if you're a FedEx guy? Was I expecting something?
I don't know what. But people had told me, when you go to MIT, you meet this guy, Alex, be prepared for the unexpected, and sure enough.
There you go.
That was the first conversation.
I'll get you back for that. Don't worry, it's coming. Anyway, so Shoya and John Hart, they were contemporaries, but personifies and exemplifies ADHD plus CDO. So he can focus intently on umpteen things at once, which is really good, and you're going to see that here. Anyway, so he finished his doctoral thesis, did all kinds of amazing, wonderful things. The most important thing is to remember, and this story is going to continue, is I always invite students up to my house, like for Thanksgiving, who have no Thanksgiving home. I can't do this year because I have no home, because we're moving. I just might. We'll see what happens. And they always do things. And I don't think he ever threw a Frisbee before. He was that analytical. And he's the Frisbee. The folks are playing Frisbee, and it goes right up on the roof. And I said, you're going to have to go get that. And I was kind of joking. Next thing I knew, it was Shoya on the Roof, not the musical.
That too is coming, but yeah.
And I took a picture, and he was deathly afraid I was going to send it to his mother. So with that, Shoya, take it away.
Well,
he finished and went to Michigan.
Oh, thank you. Thank you, Alex, for the Shoya on the Roof introduction. Thank you very much. Thank you for this awesome opportunity for me to come and talk to all of you about a bunch of interesting technologies that we've been developing. What you see on the screen, I think these things look very different. On the upper right is a handheld surgical robotic device. On the lower left is a technology that we've developed for motion sickness mitigation in moving vehicles. On the bottom right is a nanopositioning stage that we've developed for inspection in metrology in the semiconductor industry. While they all look different, the common theme here is that we try to work on research and innovations in a university environment and leverage them to develop solutions that can address a market need, a societal need, an industry need. And that's a common theme. Now, I'm going to try to cover all of these. I'm bad with time management. I may not be able to go through all of them, but let's give it a try. The most important thing I'd say is, in doing any of these things, it's important to have fun. Any of you know who said that? It's fun to have fun, but you need to know how? Other than Alex. Who? Who said that? You said that? Oh, well, it's Dr. Seuss, Cat in the Hat, right? Yeah, Dr. Seuss. It's fun to have fun, but you have to know how. Now, I don't want to scare you with this, but clearly this guy did not know how. That is not a mugshot, and I haven't been to jail, not so far. This is a photo from the day I defended my PhD in this room in 3270, 22 years ago. Okay, so, but since then I've moved, and I have ended up creating a research lab at the University of Michigan and a bunch of technologies that have resulted in startup companies. all of that through that journey, you see I've evolved, right? So I have figured out how to have fun, but most importantly, I have figured out the importance of having the right kind of partnerships if you want to accomplish meaningful things. With that, let me jump into the first technology area, which is surgical robotics. Now, you all here, you're design and engineering nerds, you understand robotics, and you probably have seen these kind of numbers of what impact robotics has had on healthcare over the last 30 years. And these numbers are impressive, but they still tell only part of the story. So more than 10,000 robots installed around the world, 3 million procedures being performed per year, hundreds of startups and companies in the space, thousands of papers and publications, and so on. Again, this is only part of the story. 5 minutes down the road, I'll tell you the other part of the story. But one thing that's important here to question is, why robotics? Like, other than the fact that as geeks and nerds, we like to design robots, but what is truly the need from the market, from the surgeon, from the hospital? So to answer that question, let's look at the issue of minimally invasive surgery, and that too in the abdominal space. So abdominal space is anything that happens between the diaphragm and the pelvic region. This is also called soft tissue surgery. A lot of delicate organs in this area, and the bulk of surgical procedures happen in the abdominal space. So talking about abdominal surgery, the old-fashioned way of my grandfather's, so my parents, surgery was performed in an open manner, like you see here. And obviously, this is a pretty gory way of going through a surgical procedure. The contrast to that is minimally invasive surgery, which is what you see on the right-hand side. In this case, the surgical procedure is carried out by making tiny incisions on the abdominal wall. The incisions look like this. And when everything is done, there's lower scarring, blood loss, there is less pain, less chance of post-operative infections, and the patient goes back home sooner and quicker. So needless to say, anyone, I hope no one has to go through surgery, but anyone, if they do have to go through surgery, they would prefer minimally invasive surgery. But how is minimally invasive surgery done, or traditionally, how has it been done? The process of that is called laparoscopy. And this is the setup. The patient is knocked out, the abdomen is insufflated with carbon dioxide, and then through those tiny incisions, the surgeon goes in first with a camera. So the two key aspects of laparoscopic surgery, there's a camera that takes an image and projects it on a screen that you see up there. So the surgeon needs to be able to see inside the patient's body, and since the body is not cut open, you make use of a camera like this. It's called a laparoscopic camera. And, these are the various components of that. But on the other hand, you have instruments that are used to carry out surgical tasks like cutting and dissection and suturing and stapling and so on and so forth, right? So that is what a laparoscopic surgery setup looks like. Now, the instruments that have been used traditionally in laparoscopic surgery look like what you see on the screen. In fact, one of the names used for these instruments is straight stick. But they literally are straight stick. They lack wristed dexterity, right? There is no wrist degree of freedom, and there's a whole bunch of companies that make these kind of products. The challenge is, with the lack of wristed dexterity, access becomes very, very difficult, and I'll show you on this slide. This is, men have prostate, and, well, many of you may not realize you have a prostate, but someday you will. I found out 3 years ago when I got my first prostate exam. It was not fun, but until then, it's buried deep in the pelvis. So it plays a certain very important functions. But what happens is, over time, 1 in 3 men will have an enlarged prostate, and as a result of that, what happens is the flow of urine becomes restricted because the prostate surrounds the urethra that gets constricted. That's just when it expands. But over time, for some people, 1 in 7 or 1 in 8 people, the prostate gland can get cancer. In fact, prostate cancer is the second most deadly form of cancer for men. Number 1 is lung cancer. When that happens, you have to go inside and remove the prostate glands. You go in and you carry out fine dissections, remove the prostate, and whatever is left, you have to suture it. You have to tie it all back together, and then the procedure is done. Now, in a scenario like this, if you were to be using the traditional laparoscopic instruments that I showed you on the previous slide, imagine how difficult the access is. This is deep in the pelvic cavity. The prostate itself is the size of a walnut. To be able to go in there and carry out the kind of steps that you see on the left-hand side is very, very difficult. Now, certain surgeons get good at it, and they're still able to do this. But again, it's difficult. And one key aspect of a surgeon performing laparoscopy is you'll notice the really awkward angles at which the surgeon has to operate in terms of their shoulder, their elbow, their wrist, very difficult convoluted angles of the wrist. This is real, these are real photographs of surgeons who are performing laparoscopy. And that represents another key challenge. So one was difficult access. The other key challenge with laparoscopy is the ergonomic strain that it places on surgeons. So given that, that's where robotics comes in. So I started this out with a question, like why robotics? Like what purpose does robotics serve in minimally invasive surgery? Well, robotics ends up enabling minimally invasive surgery by one, offering wristed dexterity. You still have instruments that look like a tool shaft that enter the patient's body, but now you have additional wristed degrees of freedom. You also have a setup where the surgeon is sitting separate from the patient and doesn't have to do the kind of acrobatics that you saw in the previous slide. There are other challenges. There's cervical issues that happen here, but in general, there's the convenience of just sitting and being able to carry out a procedure. This is a master-follower system. Whatever the surgeon does with a control joystick here gets replicated at the robotic arm. And then you have a very nice immersive imaging system. So all this combination ultimately enables minimally invasive surgery, and that's the promise of robotics. Now, the problem is, if you look at the cost and overhead of the system, it's massive. Like what I'm showing you on the screen is the Da Vinci system, and there's many other of such systems that are out there. But a Da Vinci system, there's capital cost, there is an annual maintenance cost. When you buy something this massive, you have to pay into annual maintenance. There's per procedure consumable cost. Just the process of acquiring and maintaining it is extremely onerous. It's a very large size footprint and size. In fact, you have to reconfigure the operating room entirely to be able to accommodate a robot like this. The acquisition installation process is painful. And then once you get it, the surgeon training, hundreds and hundreds of hours of surgeon training is needed before they can use it proficiently. In fact, a lot of that is also because of liability reasons. Now, that said, remember I said in the beginning, surgical robotics has made a huge impact, and that's only one part of the story. Let me wrap up that story here by telling you how much or what the reach of surgical robotics has been. These are somewhat dramatic numbers. You see total 10,000 or more than 10,000 robots that have been installed around the world. 2/3 of them are in a single country, which is the US. And everywhere in the rest of the world, see how the numbers drop. This is number of robots installed per million population. So the per capita penetration of the current robotic systems is extremely poor. It's extremely poor. And what that means is, of the 30 million procedures that happen right now in the abdominal surgery space, less than 10% are done using these kind of robotic systems, and more than 25 million procedures are still waiting for a solution that is a viable solution, that's a practical solution. And it is in that context, a lot of our work is motivated. In fact, this is Intuitive Surgical, but there are numerous other companies that have tried to come up with Me Too products. They just offer a slight variation of the same architecture, but fundamentally are the same type of solution. The healthcare system is still waiting for a better value proposition, and that leads me to this particular slide, where if you look at the cost complexity on one axis and the functionality like dexterity, ergonomics, and so on another axis, you have low cost, low functionality solutions, you have high cost, high functionality solutions. But what does the market really want? The market does want wristed dexterity to be able to achieve better reach. The market wants surgeon ergonomics, because that is a true pain point for surgeons. Integrated imaging. Of all the systems I showed you, imaging is integrated, but that's a nice to have, not a must have. Beyond that, you want a solution that fits into an existing operating room setup, as opposed to repurposing the entire operating room. You want a system that is affordable, scalable, and easy to deploy, right? So that begs the question, well, can you fill this quadrant? And is it worth a try? Right? Now, when there's a question, is it worth a try? What's the answer? Yoda has an answer, right? What does Yoda say? Yeah, do or do not, right? There is no try, right? So this is not a rhetorical question. What I'm going to show you next is we have addressed this particular quadrant on the screen. Let's see if the video plays. Okay, so you see now a surgical instrument device that provides all the wristed dexterity, right? That allows difficult reach and difficult angles. You would think that this kind of functionality is being achieved by a massive robotic system, but it's not. All of this is produced by a compact handheld robotic system that provides all the necessary degrees of freedom in a scenario where the surgeon is standing right at the patient bedside as opposed to being 10 feet away from the patient. Let me pause this right here. This is an important thing I want to point out. You know what happens in degrees of freedom, not all degrees of freedom are created equal. When we talk about wristed degrees of freedom, there's yaw, there's pitch, and there's roll, but the roll has to happen not about the axis of the tool shaft, but it has to happen about an articulated axis, the axis of the end effector. Why is that important? Because when you're trying to, for example, do suturing, by the way, suturing is the most difficult thing that a surgeon does in minimally invasive surgery, because, you know, a procedure is performed, you go inside, you do the necessary dissections, you remove anything that is cancerous, but now you have to suture everything back together, like it's called reconstruction. So you do all of that. And when you do that, suturing at difficult angles, you know, this is a difficult angle where the cut is almost orthogonal to the tool shaft, and therefore the ability to roll about an articulated axis is vital, because that is what allows you to drive the needle. Let me see if I can get back here. That's what allows you to drive the needle at that angle, right? So with this, you know, this is just the technology, but again, all of this has now been implemented extensively in a clinical setting. So I'll show you a clinical video. I hope this doesn't make you throw up, but it's a side-by-side comparison of the Da Vinci robot on the left-hand side and a handheld surgical robotic device that we have developed on the right-hand side. In fact, the early generation of this is called FlexDex. I want you to pay attention to, one, the wristed dexterity, how critical that is, and also what I told you about the articulated roll, the fact that you reach a difficult area, but then when you're driving the needle, you have this ability to articulate and then rotate about that articulated axis. This particular procedure, by the way, you're all very young. Do you know what this procedure might be? Hernia mesh. Yeah, hernia mesh, exactly. This is a hernia mesh. And, you know, the hernia mesh has to be located inside, has to be sutured in place. And then this is called closing of the peritoneum. And so extensive suturing is required, difficult suturing. What we have now demonstrated is parity in terms of wristed dexterity, surgeon ergonomics, and clinical outcomes without the need for a massive multi-million-dollar robotic system. All the core functionality is captured in a compact handheld device, handheld system. So how do we go about doing that? There are major technical challenges that we had to overcome. One of the key things that I'd mentioned earlier was surgeon ergonomics. So if you're looking at a handheld architecture, the interface between the user and the device is very, very important. Now, this is an example of someone using the traditional straight stick instrument that doesn't even have any dexterity, and you see how the movements are awkward. There are certain other handheld devices that have been developed that do offer articulation at the end effector, but the user interface is conceived in a manner that the ergonomics is still very, very difficult. Kyra, Rico says hello, by the way. This is your brother, okay?
You side profile, wondering.
Yeah. So the key aspect here with existing handheld instruments is ergonomics is very poor, usability is very poor. And you ask the question, why is that the case? If you look at this, there's a significant kinematic incompatibility between the user and the device. In this instance, what you see is, if you look at an instrument like this that has an articulating end effector, so this is the output joint, it also has an input joint, but the device input joint and the user's input joint are separated in space, right? And this is what leads to a kinematic incompatibility between the user and the device. Ideally, you would want to co-locate the user input joint, which is the user's wrist, and the device input joint. But the question is, well, how do you locate a joint where you already have bones and flesh and tendons and so on? Well, 2007, perhaps that's where all of you learn mechanisms and virtual centers and remote centers of rotation and so on. So remote centers to the rescue, right? You've all driven cars. You know that you can design a linkage mechanism that projects a center somewhere out in space, and the car rotates about that center. So you don't need to have any physical mechanical components to be able to produce rotation about a remote location in space. Anyone knows what is that linkage called? Ackerman, yeah. So we all, in a basic linkage class, you learn that kind of stuff. But I'm impressed, dude. Good to know. Here, at least for my classes, I hand out treats, but because not everyone answers that question, by the way. So you have virtual centers right now. How do you go about conceiving a virtual center design? In fact, not just that. Let's start thinking of this as a device user architecture where you're conceiving the two as part of the same biomechanical system. What you have here is, again, a device with a frame with an output joint. What we want is the handle of the device with respect to the frame. You want that joint to be one that offers a virtual center of rotation that collocates with the user wrist. But not just that, you want a mechanical system that allows you to, or that enables the two rotations of the wrist to be mechanically separated into two individual rotations, because the moment you do that, you can then transmit those individual rotations as far as you need to transmit them. Otherwise, transmitting the combined rotation of a wrist is very difficult. So we go about doing that using a constraint map approach, where what we say is, you start, if let's say you have a frame and you have a handle, and you build a set of constraints and some intermediate inputs or bodies, where between the yaw input and the frame, you look for a constraint that allows yaw rotation but constrains pitch rotation. Conversely, another pitch input which allows pitch rotation but limits yaw rotation. And then on the other side, you mirror this arrangement. What this ultimately leads to is that between the handle and the frame, you get your 2 degrees of freedom. But these 2 degrees of freedom, one of them shows up here and the other one shows up there. This is a bit esoteric. I'll show you what it appears in a physical embodiment. But before that, let me also mention you can flesh out this constraint map a bit further. The importance of a constraint map like this is it serves as a genotype. It serves as a blueprint for numerous designs that you can produce. So these resulting designs, they all look different. These are the phenotype analogs resulting from that genotype. Each one of them follows that constraint map approach, even though it looks different. But in each instance, you find there's a frame, there's a handle, the pitch input, the yaw input, and the connections are such that, for example, in this case, this particular body only rotates about pitch, but constrains yaw. This body rotates about yaw, but constrains pitch. And the constraint patterns are reversed here and there, right? So now you have multiple genotypes. You now have to take the next step of, some of these are viable, some of these are not viable. There's some practical considerations in terms of transmission stiffness problems here and in terms of too much interference there. So far, the design process is qualitative, but the next step in this process is now to look at the selected concepts that do appear promising. Now we have to jump into more quantitative analysis to truly understand the mobility behavior of these mechanisms. So there are 3 of these mechanisms. We make use of constraint theory, and this is, thanks to Marty and his former student Jonathan Hopkins, who built the foundation of screw theory, used screw theory, and developed a design tool that can be used to analyze freedom in constrained spaces. So for each of these, you can determine what the freedom in constrained spaces are. It's a bit messy, but still for this particular mechanism, if you carry out the constraint analysis, you'll find that there are 2 rotational degrees of freedom, F1 and F2. Similarly, F1, F2 here. Similarly for this design, F1 and F2. But that's not enough. You have to evaluate these designs also in the deformed configuration. Because in the deformed configuration, what happens is, do these degrees of freedom, do they change their location? Do they change their nature? What was a pure rotation has now become a screw, right? So it's a combination of rotation and slight translation. In this instance, after deformation, the constraint behavior or the degrees of freedom is preserved. In this instance, what's interesting is in the nominal configuration, this said 2 degrees of freedom, but in the deformed configuration, now it's showing only 1 degree of freedom, which is a very important assessment that otherwise you wouldn't have made just by looking at the conceptual design. What you do here in this case is, if you look at this carefully, the reason you've lost a degree of freedom is these flexure strips that you have included here, they don't allow for any twisting. The moment you introduce twisting, the moment you count twisting in these flexure strips, you can redo this analysis and you can show that this does offer 2 degrees of freedom. And I'll just show you what that means from a flexure strip design standpoint. This is a machine element that is used in that particular mechanism. Here, what is clear is, this is a constraint, that is obvious. That's a constraint, that's obvious. This is a degree of freedom like flexing and bending, that's obvious. That's a degree of freedom, again, that's obvious. But the twisting part, is that a degree of freedom or is it a constraint? And the fact that the constraint analysis told you earlier that if you made these joints extremely stiff in torsion, that particular mechanism is going to jam. So you intentionally make use of elastic averaging to achieve certain compliance in that rotational direction, and that enables the feasibility of that particular design. And just by looking at it, it's hard to do that unless you carry out the proper analysis, but now you know that elastic averaging has to be used. You can go ahead and do the geometric optimization of the dimensions. So that actually leads to a design that is workable, and show you what this looks like. Remember how I said in one direction, this is, let's say, the yaw pulley, it transmits, well, okay, it's flipped now. This is the pitch pulley, it transmits the pitch rotation, but this particular strip is flexible in the yaw direction, and effectively what you end up doing here is you do a mechanical separation of the combined yaw and pitch into yaw only here and pitch only there. That is on top of providing a center of rotation that's co-located with the user wrist, and that leads to a scenario like this where you have complete harmony between the user and the device, where there's no awkward motion of the shoulder or the elbow, anything like that. You have achieved the 2 degree of freedom transmission capability that we were looking for. Let me move on to one other important aspect here, and that is, so far I've just talked about the kinematic continuity, but separate from that, where is the effort coming from to drive these degrees of freedom? So the yaw and pitch, if a human is driving the yaw and pitch, all of those muscles are in your forearm. And the forearm is like, gross motor muscles. I mean, this is like a good, strong volume. However, when it comes to the roll degree of freedom, how do you drive the roll degree of freedom? You can drive it by pronation, supination, but there, the range of motion is limited. You can drive it by your fingers, but fingers are driven by small motor muscles that are captured in your palm. What that means is, this is leading to a scenario that if you want good surgeon ergonomics, can we create a system where there's shared actuation, where yaw and pitch is coming from the human motors, which is human muscles, but the roll is coming from a motor or a power assist system. So with that, once again, we lay out a constraint map. I won't jump into the details of this, but I'll show you a schematic that, again, this is the genotype and this is the phenotype, and you can produce multiple different phenotypes. But what this shows is that you can have articulation inputs coming from the handle, and those articulation inputs come to these 2 inputs. These 2 inputs drive a swash plate, a swivel plate, that takes the tip and tilt and yaw and pitch rotation that is coming in. But then you have another swash plate that inherits the tip tilt of the first swash plate, but the second swash plate is a rotating swash plate, has also the ability to rotate. Now that swash plate is driven by a motor, a roll motor, and this part is the servo control. This is the part that is driven by the fingers. That is the part that is being driven by the wrist. Now this being driven by fingers rotates the tool shaft. The tool shaft is coupled to the rotating swash plate, and that also causes the rest of the transmission system to rotate in sync with the roll motor and so on. So when all of this is implemented in an actual design or a physical design, this is what happens. So you see the wrist actuation, this is actually human power coming from the forearm, but the roll here is coming from a motor back there, and that motor is driving this pulley, this coupler arm. Back here, there's one swash plate, which is a non-rotating swash plate, and here there is a rotating swash plate. Does this remind anyone of any mechanism that you have seen in the past? It is actually a very common mechanism. Helicopter rotor blade pitch control. Effectively, what we have done is we've taken, and by the way, remember I was talking about the articulated roll. The articulation here is being achieved by the wrist motion, and the roll is being achieved just by fingers driving a servo system that controls the motor. So effectively, what we've done is we've taken a helicopter pitch control mechanism, and we've miniaturized it and captured it into a tiny matchbox size portion of the device, and this then helps us achieve all the requirements that we were looking for in terms of surgeon ergonomics. There's a whole bunch of other mechanism designs here. I'm going to skip through this. I'll run out of time otherwise, but I'll skip through all of this. Let me get to the all of these technologies, ideas being combined and put together into a product. Ultimately, this is what it leads to in a surgical setting. This is the device, that's a device, that's a device. And in each instance, this is enabling complex suturing and reconstruction. I'll show you some more examples of clinical adoption. This is a hospital system in a rural community hospital in Michigan, where the surgeon, Dr. Ken Bowden, has conducted more than 1,000 surgeries with this particular device. This is the financial impact of using Da Vinci versus a device like FlexTex, which I showed you, where the contribution margin is effectively the profit margin that the hospital makes from what it actually spends versus what is covered by insurance. And again, there's more and more examples. This is another community hospital in Wisconsin, where Dr. Peter Janu has done hundreds of procedures with this. Eventually, over time, this technology started to spread all over the world. This is a case of a surgeon using this in Ireland, publishing this in paper, conducting controlled studies. These surgeons, I don't know any of these surgeons. This is stuff that I know because I see the work appear in clinical journals. What is remarkable for me is that the value proposition that we had created and we had offered and that we'd written into our proposals, now we see the end user, the surgeon, writing that value proposition in papers that they publish. This is that procedure, radical prostatectomy, I told you about earlier. These are instances of surgeons performing this. Again, many different locations around the world. In particular, US Air Force bases, important area where you need affordable, accessible surgical technologies. This is an instance of partial nephrectomy where the kidney could have cancer. You remove a tumor from the kidney and the rest of the kidney has to be sutured shut. It's called partial nephrectomy. Again, used in the US as well as this is NHS in UK. And again, these are not my work. This is what the surgeons are publishing in their own papers. More instances of partial nephrectomy, more instances of bariatric surgery is a procedure where you bypass the stomach and you connect the esophagus to a portion of the small intestine. So there's a lot of suturing that is required here. Again, instances in Australia, Netherlands, Turkey. Whipple is a very complex procedure. Whipple is a procedure where if someone has pancreatic cancer, then a whole bunch of the pancreas and organs have to be removed. And again, a lot of reconstruction is needed. So these are procedures in Australia, Belgium, and again, surgeons talking about the efficacy and viability of this in terms of offering them an alternate to the big robotic systems. If you happen to be the dog of a rich person, then there's some instances of vet uses as well. These are the countries where the technology has been used. More than a dozen countries, thousands and thousands of procedures have been performed, but now we're bringing yet another generation of that technology and focusing on India and China. But again, this kind of thing takes a village. I'd say it takes a zoo. There's a very big team that I ended up working with. So I ended up starting a company called FlexTex. Many of the employees here are students from my own classes. So I did offer a job to Kyra. He turned it down and ended up coming to MIT. Same with Adam. The best students in my classes, I offer them a job at my companies. Sometimes they join Other times they end up at MIT. A lot of media coverage, all of this is fine, but the thing in media coverage I wanted to tell you, the best headlines come from tabloids. I don't know how tabloids, get this, but this is British tabloid. Their choice of words, pioneering one, Robocop arm. I mean, this is just delightful to read. But jokes aside, the reality is that this was a procedure performed on a little kid, and to know that something like this is impacting a family, a child, half around the world is gratifying. All of this is great, but I have to tell you this, that the ultimate sign that somehow your technology has been noticed comes from the sound. Okay, so I have to tell you that my daughters, I have two daughters, they take a dim view of me. They think I'm a balding middle-aged man was trying to figure out stuff in life, and why else is he working so hard all the time? But so they don't care much about the media coverage and so on, but they are voracious consumers of Netflix and streaming. So there's a lot of crazy things that have happened, but this has got to be one of the craziest. So this is a show called The Resident. I didn't know this, but somehow this happened. And then, my daughter pointed me to it, and I went and watched, and of course, they're having a deep conversation about life. I just wish that this lady was using the device properly. She was, showing off. But good thing for me is I was able to get some acknowledgement from my kids, which is, for anyone who has kids, getting that is kind of a tough accomplishment. So anyways, I really need to move faster. So a few things I'll say here is there's about a dozen technical innovations that were packed into that device that I didn't go into. But at a high level, we addressed kinematic compatibility. We addressed shared actuation and control. And the third aspect of what we're working on now is bidirectional communication. One of the challenges that happens in surgery is there aren't enough expert surgeons to train the residents and the novices. So what we're doing now is we are packing the device with inertial sensors, so motion detecting sensors. And what that does is we let the surgeon use the device over a given procedure. We let an expert surgeon use the device and generate a motion profile. And you collect that data across hundreds, potentially thousands of surgeons, and you establish what is an expert usage profile, right? And then you use that data to train novice surgeons, and that training happens by virtue of haptic motors that you embed on the device, that if the surgeon is misusing the device, if they're lifting their hands or moving their hands too much, they immediately get haptic feedback. So now this is the third layer, and all of this, what I find is this is an incredible confluence of mechanical or biomechanical design, mechatronic design, and data-enabled bidirectional communication between a machine and a user. And I feel like this is the kind of thing that only happens in mechanical engineering, this kind of intersection. Now, for me, this is the next stage in the evolution of surgical robotics, the kind of transformation that happened here, that I don't know how many people use desktop computers, especially to check emails, send messages, and so on. Like my parents don't have a desktop computer, but they do have, every aunt, uncle, everyone has a mobile device. The vision that we're working towards is same thing in robotics. To achieve the core functionality and value of robotics, you don't need a room-sized multi-million-dollar robotic system. The next step in the evolution of robotics, at least in this application, is to capture the power in a far more compact manner and create a system that is truly interfaced with the user, that works in a harmonious manner, that is compatible with the user, and that communicates with the user. And by the way, with all of this, we cracked open a new market segment that didn't exist after us. There are about half a dozen other companies that came out with similar products. So that's this on surgical robotics. I'm sorry, I'm talking fast, but there's at least one other technology I want to cover here. Maybe, can I answer a quick question about what I said so far? Yes?
So I was thinking about when you said the genotype and the phenotype.
Yeah.
How much is the translation from the genotype to a phenotype, like human-inspired versus like computational?
So that's a great question. Right now, human-driven, but this is something that can be very much automated, because what you do is once you define the characteristic of a constraint element, right, that it should constrain so many degrees of freedom and allows other degrees of freedom, you can have a catalog of machine elements, right? How did I or my students generate those multiple phenotypes? Just because of the cataloging that's going on in our mind, but that process can be automated. Again, we haven't invested the time and effort to automate that design process, but it can be done. Okay, let me talk about motion sickness. I know this is kind of a goofy thing. A lot of people don't think about motion sickness, but my kids complain all the time. When I drive, my wife complains all the time. About my driving, but I think it's also motion sickness. But it is a real issue, especially right now in the context of autonomous vehicles. Motion sickness has become a real issue, and you can look through the literature, both media like this, like Forbes and Big Think and New York Times and so on, as well as academic literature that points out the issue that in self-driving cars, motion sickness is going to be significant. In electric vehicles, motion sickness is going to be significant. Why so? Because the regenerative braking induces higher degrees of accelerations. Again, when you are sitting, in a ride-sharing kind of scenario, motion sickness is higher. So ACEs stands for automated, connected, electric, and shared. So that is the future of mobility. And in all of those cases, human factors is a big part that doesn't always get addressed as adequately. But again, we ran into this issue about 5 years ago. Kind of an accidental kind of thing. But once this happened, we asked the question, like, why is it? By the way, the incidence of motion sickness is 1 in 3 adults and 1 in 2 children are prone to motion sickness. So the question is, worth asking is, why does motion sickness happen? And do we know any instances where it doesn't happen? So you may all have this experience that if you are driving a car, the driver almost never gets motion sick, right? But the same person, if they're a passenger, they will get motion sick, right? So let's carry out this scenario. Let's say the driver takes a right turn. The driver knows that I'm going to take a right turn, and you know what the driver does? They lean into the turn, but the passenger doesn't know what this dude is going to do, and the passenger ends up reacting to the inertial forces that happen in the car. And in fact, if you're sitting in the second row, you have even less awareness. And you sit in the third row of a minivan, that's where kids throw up the most. So it is an aspect of awareness, a lack of knowing what is going on. So it's a combination of anticipation, but that's not all. It's anticipation and preemption, right? Because the driver knows what's about to happen and they do something about it. In fact, simple thing, when the driver hits the brake, they know that the vehicle is going to decelerate, and they actually lean against the steering to sort of stabilize their torso and their body, versus the passengers don't, and the passengers end up moving around quite a bit. That leads to motion sickness. So we said, if it's just a matter of anticipation and preemption, can we create a system that replicates this kind of behavior? You can predict what's about to happen. Prediction algorithms are very strong. You can predict the right turn is coming up. And if you make an accurate enough prediction, you can lean a seat into the turn so that the gravito-inertial vector is aligned for the passenger, and all passengers, non-driving passengers, end up behaving the same way that the driver behaves in a traditional car, right? So we thought this was, again, it's an interesting thought, and we got to the idea that it's a big unsolved problem. So we said, okay, is it worth a try? And the same answer, well, nothing tried. Let's actually build a system. So the core innovation here, we call this technology Preact. Preact is a prediction software, and the software makes use of extensive amounts of data to predict what's about to happen in the future. And based on that prediction, Preact engages various different types of hardware. It could be stimuli, it could be an active restraint, it could be a seat, to preemptively make some corrective action. You know why it's called Preact? Instead of reacting, you're preacting, right? I mean, it's like, I don't know, you folks are young here. Anyone watch the movie Minority Report? No? Tom Cruise? No, you're here. So you know what happens in that movie. So there are 3 precogs who can tell what's about to happen in the future. And Tom Cruise collects that report, and based on that, they go ahead and preempt the crime before the crime has happened. This is exactly what we're doing. So again, the idea seems interesting, but does it work? Well, we said, let's build an experimental setup. We acquired a van, and we set it up. a computer cabinet with auxiliary power. We got a tip-tilt seat. It's a gaming seat. We got a seat cushion with haptic motors embedded in it, a lot of electronics, embedded controls. We set up an extensive set of data acquisition system to measure all kinds of states of the vehicle, the seat, the passenger, and by the way, this is again your GSI. This is Daniel, by the way, behind the mask. You have IMUs, you have SEMG for muscle action, you have physiological sensor via that watch. There's Aruco markers. You collect a lot of data to figure out what is going on. This is MCity. MCity is a test track at the University of Michigan where you can conduct experiments. So we created this path that emulates highway driving and city driving, and you try to get a bunch of start-stop events and try to match the acceleration levels. And you do the appropriate triggering of the pre-act system prior to the inertial event happening. We set up a human subject study, so we had to go through an IRB. And in the study, we would recruit human subjects and we would ask them to report their level of motion sickness every 90 seconds. Again, a lot of measurements. And it turns out that the thing works. I mean, this is the result of one of our studies that is showing a drop in motion sickness. This is self-reported motion sickness scores that are recorded every 90 seconds. A substantial drop in motion sickness. In fact, I'd say one of the strongest experimental evidence we've seen anywhere in any published research or data. And this is qualitative, but then separate from this, there's also a quantitative aspect, which is you can measure electrodermal activity through that watch that I mentioned earlier. And there's a remarkable drop in electrodermal activity, which is drop in perspiration. In all, we have now, in the last 5 years, conducted 4 studies, more than 150 human subjects. A very strong, so this is a p-value of less than 0.1 is the probability that all of this is a random effect. So a low value of p simply indicates that this is not a random effect, that this is statistically significant data. Of the human subjects we asked, would you like this? And more than 85% of them say yes. Also, we make them perform tasks like, solve a crossword puzzle and read stuff and so on and so forth. So there was improvement in tasks. Now, once you have data, what do you do with data? You train models, right? You train models. That's what so we have access to incredible amount of data. And what we do is this is all the sensor data. This is the output. These are the inputs. You go through a certain level of data processing. And there's standard machine learning algorithms that are packaged for mechanical engineers like me, where we can input the data, we can optimize the hyperparameters, and we can produce some very interesting results. So this is NARCS. NARCS is a nonlinear auto-regression exogenous recurrent neural network, which is, again, a standard package that my student has used. And one of this is the actual motion sickness, the other is showing predicted. Here, this is confusion matrix. This is basically class prediction, like a binary determination of based on certain just objective measurements of, let's say, head motion or electrodermal activity. Can you predict accurately whether motion sickness happens or not? So we develop all of these models because ultimately this gives us the ability to create the algorithms that we will use to generate the preemptive commands for either haptic seat or a tip-tilt seat. So we use these models, and there's a lot of interesting design insight that comes out of this. Well, let me move through this slide because I want to go through the rest here. The key thing here is we ended up, all of this stuff happened, and we, showed up again in the media. We were, I think, in the Wall Street Journal recently. So we attracted a lot of attention, and of the industry partners, we ended up getting approached by Toyota, who happened to have a seat like this, and it was a passive seat, and they said, hey, we are working on these suspension seats on one end and motion sickness on the other hand. Seems like you folks are doing something interesting, and can you help deploy pre-act system on our vehicles, our devices? I said, well, should seats have degrees of freedom? They said, yeah, roll and pitch. I said, boy, you got to be kidding me. I mean, these kind of degrees of freedom and mechanisms like this is what we do. So all we did in this case was we equipped the seat with active motors, and the active motors were then preemptively triggered. And again, we ran a study, first in that closed test track, excellent results. Now, in fact, this month, actually in November, December, this month and next month, we are running for the first time Preact on public roads, and we hope that the results turn out to be good. One of the key things that happens, some of you might be budding entrepreneurs here. We work in the technical domain. We design mechanisms and machines and mechatronic systems and robotic systems and so on. But ultimately, for a product to succeed in a market, you have to have the discipline of mapping out how does the value flow of your product to an end user. So in case of the automotive value ecosystem, it's a difficult one. It's a complicated one. What we develop here, we are working with the automotive OEMs, and at some point they'll pull in the automotive suppliers, and ultimately that value will reach the passengers and riders. Similarly, I didn't show you a similar value ecosystem for medical devices. It's even more convoluted there, but understanding that and optimizing for that is key to successful product development. In this case, one thing that happens is because we're working with Toyota and they are excited about this, it still is going to take them 3 to 5 years for the technology to show up on Toyota vehicles. In fact, the product that's going to be launched 3 years from now is already frozen. You can't add anything to that. In the next cycle, we might be able to add the Preact system. Now, what happens is, if we look at what does the primary beneficiary say, what do the passengers say? So I'll show you test results. This is what actually people sitting in this Preact system are saying. These are
I think the seat movement side to side is really nice. If I was gonna buy a car, I would probably buy it. Yeah, to a large extent.
That's what you want to hear.
Side to side, I don't have to focus on steadying myself. So then easier to do other tasks without getting motions.
Oh, it was definitely positive. Helped a lot. I think a lot of it was psychological as well, because the seat was telling me where the car would go.
So this is once again the value proposition that we create
And that
we write in our proposals and stuff. You hearing that was the end user, which is a strong validation.
Last time I mentioned, when the card was taking turn, I was taking longer to think and to read the paragraphs or find differences in the images. But this time, since the transition was so smooth, especially side to side, I felt as if the car
The side to side is the
motion sickness.
roll motion.
I would say I was relatively nauseous the first time around when the seat was.
But anyway, this keeps going on and on, okay? So the key thing, the reason I wanted to point this out is if you have a strong pull from the primary beneficiary, and if you have the ability to deliver the value directly to the primary beneficiary, that is the strongest way to validate a technology and whether it sticks in the marketplace. So is there the ability to take this and deliver directly? Luckily, there is. In fact, my PhD student who was working on this decided to create a company on the Preact technology and called it Motion Sync, because you're synchronizing the motion of the user, of the passenger, with the motion of the vehicle. And sure enough, he captured the core aspects of Preact in a hardware package here, which is just a lumbar support pillow, and all the software runs on an app. And just between these two things, this becomes an aftermarket product. You don't have to work with any tier 1 or OEM or anything like that. You simply buy this system here and you install an app. And they've developed the app. The key aspect of the system is the phone app works here, and this is the pillow right here. It has a microcontroller that drives the haptic motors, and they send commands to the vibration motor. And basic set of modules, but the computation, the prediction of what's about to happen in the future is happening on the phone app. There's a slightly more advanced version of this where you also have an onboard camera, a dashboard camera, and you can collect even more real information. And there's a bunch of computer vision algorithms that can run on this local microprocessor and send information to the phone app as to what's about to happen. And again, this shows a data processing pipeline through multiple information sources. You can do feature extraction You can run a bunch of algorithms. Much of this is coming from the camera, dashboard camera, which is, like object detection and depth estimation and lane segmentation and so on. And you do sensor fusion, and based on that, you send a command to the haptic motors to vibrate ahead of time to inform the passenger that something's about to happen. This is a plug from Daniel. He said, Shaurya, please show this slide. So this thing is going to be out in Q1 of next year. But kidding aside, this is the only thing I want to mention here. It's something that is ready for deployment now. Again, it takes a zoo. It takes a big zoo. Adam, this is what you looked like 5 years ago, right? You were a kid. So Adam contributed, who's now a PhD student with Professor Dave Trumper, right? Yeah, he was part of this team. There was more than 50 folks who participated in this. And again, an incredible effort. The remarkable thing is that for the people who participated, this is the ultimate melting pot of diverse backgrounds. We had people from IOE, Industrial and Operations Engineering. We had folks from mechanical engineering, electrical engineering, computer science, robotics, and all of these folks contributed to making this happen. Again, I feel like this kind of thing can happen only, or maybe I'm biased, but I feel this kind of thing happens in mechanical engineering, where you have a physical system where you add a wrapper of sensing and instrumentation and embedded controls, and you collect data, you use that data to make predictions, and you use those predictions to bring about some positive outcome. This, to me, is the ultimate definition of DEI. So I don't know, is DEI still a thing? Well, it's always been a thing for us. For us, DEI is this, and it's the ultimate form of DEI. Design, entrepreneurship, and innovation brings people from various different backgrounds into solving problems that ultimately make some kind of an impact. I think I have to stop here. The nanopositioning systems, I'm out of time. If I stay in John's good books, maybe I'll get invited again for this seminar, and I can talk about nanopositioning stages. It's just really cool work we're doing with KLA, which is a semiconductor manufacturing equipment company. But let me pause here. I'm sorry, I'm already a few minutes late. I can answer any questions. Okay, thank you.
I'm going to do the mic for questions. Do we have any questions?
Yes, you get a lot of questions. Yeah.
Wait, we got to do this, so it'll be recorded.
I recorded, okay.
Is it on? Try to switch the other way.
Just use the Alex voice.
Opera voice.
Yeah. Yeah.
I'm so glad I attended this talk, actually. So my question
Are you looking for a job?
No,
not
it's
yet.
not for that.
Okay.
Like I got some nice ideas, actually.
Good.
So the question about Preact is, like, compared to the previous technology, which I feel is like less mechatronic, why did Preact turn out to be a lot more mechatronic and software oriented? Like, you could have thought about passive designs which were like linkage based or something.
In Preact?
Yeah, in Preact. Like, it's ultimately about tilting the seat. So why couldn't it have been more like linkage based without having to do
And then you can. In fact, to be honest, there are many mechanical solutions for providing some kind of an input to the passenger. And in fact, that is driven a lot by what the market dynamics are. So for example, there are certain seats that are created with lumbar wings, and you could just use that to gently nudge the passenger who's sitting on the seat. You can have haptic motors, you can have complete tip tilt seats. There's definitely an economic element to that, and you can optimize the mechanical and the mechatronic design for the constraints of whatever the market dynamics is. Irrespective of that, the true aspect of Preact is the data, the prediction, and when to send the command to whatever hardware you use. So from that standpoint, there was an existing seat that Toyota already had. We felt that it was just okay for now to implement that. Someday when I don't know if we want to become a seating company, but if we do, then definitely we'll come up with a clever linkage mechanism for seats.
Any other questions?
Hi.
Hi.
First of all, thank you for a great talk. And I'm wondering, in the first topic, you talk about that you want to reduce the cost
Yes.
from Da Vinci to what's the name of the system?
So FlexSticks is one, and then another one is called parallel robotics. Yeah.
Yes.
Yeah.
So in the second topic, can you estimate what will be the cost to apply something like this in a car?
Yeah. So in fact, that's part of the painful discussion we're having right now with Toyota. The costs. I mean, this thing is being recorded, so let me just give you high-level estimates. A full seat in a car costs about $2,000 to $3,000 in that range, and for a luxury car on the higher side. In the U.S., outside the U.S., those numbers are lower. So all the claptrap that you add in terms of additional mechanisms and motors and so on, if it ends up being more than a couple of $100 of additional costs, that becomes a serious issue for any automotive company. In fact, even at $200 extra cost, they are just so risk averse because, again, the timeline of validating the outcome of that investment is so long, which is precisely why we're doing this direct to customer version, because we want to create enough of a groundswell of excitement that they get feedback from their customers that this kind of Preact technology is indeed value adding, that will then convince them to invest the cost in their seating systems.
So seat heaters are an example.
Seat heaters.
It was proven that in the Nordic countries that they reduce backache because you get in your car and the seat is cold and it takes a while for the seat to warm up. And car companies would not do it, so the whole aftermarket on seat heaters. And then
That's exactly what happens. Right?
yo!
Yeah. It becomes a differentiator now. So most cars now will have seat heaters in the front two seats at least.
Okay, any other questions? Anyone? Oh, here we go.
Take care, Gara.
I have to acknowledge that I'm an average guy. I was married with my wife already 28 years.
Then you're not average. If you've been married
Yes,
for 28
but
years,
was accident that my wife had the sickness, so I was sidelined to the passenger care. For 28 years. I have to just...
So you've been sidelined by your wife for 28 years. Is that what you're saying? Yeah, I've been sidelined by my wife for 25 years. Sideline. Well, you ask.
Yes, I understand that. No,
You
I
cast
have to
aside.
have
You
no
either-
choice. Go
Yeah.
out of wheels.
Yeah.
Just go
Yeah,
right now. So
my wife
I
drives
just
my
heard
life.
this stuff. I said, maybe this is my end of my suffering.
This thing is being recorded, man. Okay.
Well, I don't care for me.
No, I care for me. I mean, these people.
Just
Sorry.
so I have to question you, when
Please.
it will be available in the car, because my wife also have Toyota.
Okay. Yeah, so to be honest, there's a version of this that's going to be available next quarter in Q1 of next year, which is a light duty version, which all it does is instead of move the seat, it provides haptic vibrations through a pillow. And those vibrations are sometimes enough to give the passenger enough of a cue as to what's about to happen. The tip tilt seat that is embedded into the car, that's at least 3 years, maybe 5 years down the road.
Okay, thank you.
Any more? I have a question. Go back to the FlexDex
FlexX.
and show us the mechanism linkage between, I'll call them,
The constraint map or?
no, the two Cobras.
The two Cobras, the flex strips. Yeah.
The flex strips, and how does your hand motion somehow couple with the flex strips to cause the motion at the tip? Where is that linkage connection?
Absolutely, yeah. So let me go over this. So in this instance, you see the hand motion right now, that is all yaw. It's all being captured here, and that is not moving at all. But now this is pitch. So pitch is all captured here, and there's no motion there, right? So the first thing that this does is, it is a mechanical separation device, right? So it takes a combination of yaw and pitch at the wrist, and it filters out yaw only here and pitch only there, right? So that's the first thing that this does. The moment this happens, now you have two individual single degree of freedoms, right? And you can wrap up a cable and route it Well, you see those tracks, and that's routed all the way through, and at the end, it's recombined. And that's the beauty of taking a combined, 2, 3, 4 degree of freedom motion. If you can separate them into individual motions, then you transmit as much as you want and recombine at the end.
So that's what I was wanting you to show is you're using tendons back here.
All the way, all the way.
Do you have a more, so you can kind of see in there, a more detail of how you actually wrap the
Yeah, that actually,
the actual hat?
yeah, let me show you.
The whole idea of tendon robotics is a very big thing.
So the tendons are somewhat visible here. Let me see.
One of the early people in tendon robotics was Ken Salisbury.
Yeah, right here, MIT. Yeah. MIT has
Kind of pre-CSAIL, but in that group of life forms.
that is true. In fact, MIT, the DNA of a Da Vinci robot traces its journey from MIT, and there was, I think, Silver Falcon or Black Falcon. So early prototypes were created right here.
So Bruce Skeena, who was one of my master's students in 1987, 88, did a huge number of the mechanisms for Da Vinci, by the way.
Wow. Okay, well, is Bruce with Intuitive Surgical or?
He's with Intuitive. He's a fellow now.
Okay.
He's still kicking.
No surprise.
And so he learned about instant centers and Ackermann linkages and stuff.
With you?
Well, a young guy back then.
It's cool.
Which I learned a lot, by the way, from Joseph Shigley and even before that, Bernie Roth. So this all goes way back.
Did I mean, I don't know, maybe the seminar is over, but I want to say this. 6 months ago, I became the Shigley Professor of Engineering at the University of Michigan. It's a crazy thing because when I was a PhD student here, I don't know if you still carry a machinery handbook with you, right? That was it was my Bible, and machinery handbook is edited, compiled by Shigley. That's in grad school when I was working with Alex. In undergrad, I learned all my machine design or machine element design from Shigley's textbook. I didn't realize that Shigley was a professor at Michigan. So they asked me, is there a Michigan professor name you'd like? And I looked it up and, well, that's Shigley, that's it.
And my chair now, the May professor, he was head of machine design at Mack Truck.
Oh, what?
I think he might have, that person passed away, but I know his grandson, he and Shigley were good buddies. So we're related in that respect too.
Too many connections.
Anyway, any further? Yeah. Oh, run up.
Hi.
So this is kind of minor question. I'm just curious because the wrist, I looked to your mechanism and I'm trying to see if maybe you felt that wasn't important, but this movement and this movement, they are not in the same centers of the human wrist. They are different centers of rotation. And you could easily adopt that in your device.
That is true.
So I was curious why you didn't do that.
Yeah, so that's a great question. It turned out, so we in fact consider that, and you're right that in this design, it's very easy to relocate the centers to exactly co-locate with the wrist. Well, we found that as long as you get into an approximate region of about a 1 centimeter radius volume or sphere, that is good enough to achieve sort of that kinematic compatibility or continuity that you're looking for. So getting to that level of precision was not needed. And therefore, we just kept the design symmetric. In fact, another issue there is, think of the range of human wrist motion in this direction versus that direction. It's different, right? So you can have two different transmission ratios going from the input to the output. But again, we just kept everything, the entire range, to be within 15 degrees cone, that we didn't have to go through that level of variation. But those are things we've captured in our patents and stuff. It didn't, to keep the product simple, it just wasn't needed. But that's a very good observation.
Anything else? Okay, to keep us on time, we have a little gift.
We have a gift.
In relating to the fusion of things, we have in the Michigan colors an MIT bag.
That's all.
Even better.
That frisky. Are you capturing this, right? Okay, right there.
There you go, baby. You can go home and sit on your own roof.
Exactly. Thank you. Thank you very much. Oh, it's a fretmark frisbee.
Yeah, it's from our lab. You know, you helped develop all this.
Yeah, it was, that's so awesome. Thank you. Thank you very much, Alex.
Less older.
We were less older, yes.
All right. Again, thank you very much, Roya.
Thank you. Thanks, everyone.